This is different to the question of where there is slip actually during the earthquake. So when we talk about locked versus creeping, that's sort of in the interseismic period, that's between earthquakes, whereas this is what's actually happening during the earthquake. Does that answer your question? Okay, so the question really is what's the cause of higher slip in some places, lower slip in others, and the suggestion was it could be related to the material on the fault, the sediments. So in this is a simulation which just has heterogeneity on the surface of the fault, and it's heterogeneity that's just defined in a statistical sense to look like fault ruptures actually look like. When it comes to what causes this variability on the real faults, we think that variability in the geology, so remember this is at depth, so there's not sediments down here, it's different types of crystalline rock. Serpentinite is one of the factors. Serpentinite is a very slippy mineral, literally, and so that affects the amount of slip that we see in different parts of the fault. But the truth is our understanding of what's going on here is really limited because it's all beneath the surface. It's very difficult to get any observations. We could drill boreholes down and poke boreholes through the fault, but even the deepest drill hole, in fact the deepest continental drill hole is 12 kilometers depth. It's in Scandinavia. Recently there was a big deal experiment in California to drill through the San Andreas fault at Parkfield, and they drilled through the fault at a depth of I think it was about 5 kilometers. So it's it's right up here. And so we have one drill core that goes through one patch of the fault that's this big at 5 kilometers depth. So we have very limited information about what's going on. That's why seismology is critical. Good segue. Because the only way we can really constrain what is going on at this depth is by recording the seismic energy at the surface and using it to then model, to image what's going on at depth. Okay, other questions? All right. So that brings us to seismic waves. Perfect. So I already mentioned the idea of these different seismic waves and the fact that they radiate from the Earth's surface at exactly the same point in time. So the first wave is the P wave. I say it's the first in the sense that it's the fastest wave, and so it arrives at the surface first. It's called a P wave actually because when people first started to try and understand these seismic arrivals, they were just looking at paper records of these arrivals, and they called it P for primary because it was the first arrival. Okay, so the origin of the term P wave is that it's the primary wave. So it travels the fastest. The way that it actually travels, the physics of the process as it travels through the Earth's crust is a compression type of wave. So that's what's being illustrated up here. The wave is obviously traveling in this direction, and the compression, you can see by the compression of the squares, is in the same direction that the wave is traveling. So that's the key thing. The particle motion is in the same direction that the wave is traveling, in this case, in this direction. Okay? So that's the definition of a P wave, is when the particle motion is in the same direction as the direction the wave is traveling. The S wave, again, S was for secondary wave. It was the second arrival when people were looking at their seismograms. And it turns out that the particle motion for an S wave is from side to side. So that, again, obviously the wave is traveling in exactly the same direction as for the P wave that we were just looking at. But the difference now is if you look at any given particle, such as this particle right here, so the wave goes by, this particle moves up and down, right? Up and down, and then back. And so the particle motion in this case is perpendicular to the direction that the wave is traveling. So that's the key difference between these two waves, is the particle motion is in the direction that it's traveling or is perpendicular to the direction it's traveling. Okay? And the second piece is that the P wave travels fastest, it arrives first, and the second wave, and the S wave travels second, the S wave is slower and arrives second. In rough numbers, the P wave travels at twice the speed of the S wave. Okay? So, I need 4 volunteers. Okay. We seem to be having all-round system failure today. Okay. All right, so that's P waves and S waves. I guarantee you that as a result of that little demonstration, you will now remember the difference between P waves and S waves, so thank you to our volunteers. Okay, so finally today I want to talk about, so now you know what P waves and S waves are, I want to talk about how we actually record them, how do we actually collect that data so we can then, analyze the earthquakes. And so I want to go back to the beginning. The first recordings of seismic shaking were obviously very basic, and they were simply using a pendulum. And so the idea here is if you hung a pendulum from the ceiling, okay, very long pendulum, and then we had an earthquake, what would you see? What would happen? So the pendulum would swing. So why would the pendulum swing? The physicists in the audience can answer this question. Should be able to answer this question. Well, shaking, but what's the physical, what's the source of the force, I guess? I didn't hear somebody said something. Say again? No? Come on, nobody in the room want to explain why a pendulum starts to move? Let me ask the question differently. What is actually moving? Right, okay, so what's actually moving is the building. So the building is attached to the ground is moving, and so the building moves with the ground. So then the fact that the pendulum appears to be moving with respect to the floor, the pendulum is actually stationary, and it's the building that's moving. And so it's the inertial mass of the pendulum causes it to stay stationary, right? So everything has an inertial mass, and in order to move that inertial mass, you have to apply a force to it. Okay, so the reason I could make this P wave is I applied a force to the shoulders of the guy at the front. In the case of a pendulum, because it's hanging from the ceiling, there's no force on the pendulum. So the building moves, the ceiling moves, but the pendulum stays stationary. And of course, over time, there is actually a transfer of energy from the building to the pendulum down the line, the string or whatever. But initially, it's the pendulum stays stationary, and the building moves. Okay, so in this sort of scenario where you have a big piece of paper on the floor here and a pen on the bottom of the pendulum, the floor is essentially going to move underneath a relatively stationary pendulum. So this is the sort of concept of using an inertial mass to measure the motion of the things around the inertial mass with respect to the inertial mass. So that's how a seismometer works. Well, every seismometer works based on this principle of there being an inertial mass, and you're measuring the motion with respect to an inertial mass that you try to keep stationary, or if it's not stationary, you need to understand how it's moving. Okay, so that was the first seismometers, and here's an example of a pendulum record from 1891, July the 19th. I actually don't know what earthquake this is. I'm sure we could figure that out with approximately 4 words entered into Google. Okay, so as time progressed, people wanted the problem with this, of course, so what information can you extract from this record? Yeah? No? Right. And then became small. So what she's saying is that there's a lot of lines in the middle, as in no motion or small amounts of motion, and then fewer lines that are around. And what she was then trying to do was sort of comment on when this relative motion may have occurred. And the comment was that these bigger swings might have come earlier and this came later, etc. So what we're missing here, of course, is the time history. We don't have a time tag on this bit of the pen and then this bit of the pen and then this bit and this bit and this bit. So what we're missing in this record is the time history. That's something obviously that we do now have. There's a lot of time when the pendulum is staying in the middle, as in very little motion, and then less time when it's out here. But what we can extract is the peak motion, right? The maximum motion, the maximum displacement of the pendulum is sort of, this is obviously the center, and I'm not sure if it's out to here, or maybe it's out to here. It's probably about the same. Maybe it's out to here. So we could extract the peak motion, and we could extract the direction of the peak motion. So this is a horizontal, obviously if this is the pendulum, this is a horizontal piece of paper. So we could determine that the peak motion perhaps is in this direction, whatever that direction is. Okay? So people then wanted to improve on this, and this is one of the oldest seismometers we have. This is actually the author of your textbook, Bruce Bolt, who was a former director of the Berkeley Seismic Lab as well. And this is a device developed in China, which has a pendulum. In the middle of this is a pendulum. The pendulum moves backwards and forwards as a result of the shaking. And then there's a lever between the pendulum and the mouths of these dragons. So when it swings in a particular direction, it causes this lever to open, and the ball drops into the mouths of the frogs that are surrounding it. Okay, very nice, beautiful, intricate device. And what this does is it allows you to see the direction in which there was strong shaking, right? So some amount of shaking in a particular direction is sufficient to cause this lever to open, and then this ball falls into the frog's mouth. Of course, it sits there. So that's the other thing. You don't have to be watching it at the time of the earthquake. You can come back, see which balls fell, and it's telling you something about the direction of the ground shaking. So this is one of the first instruments used to start to record the nature of ground shaking in earthquakes. So today, of course, we don't use that approach, but the principles are exactly the same in terms of using inertia. I think I have it right. Okay, so when it comes to recording horizontal ground motion, it's the same idea. It's the pendulum idea. The difference would be now that we have either a drum recorder. People historically think of drum recorder as a piece of paper that's just being pulled underneath this pendulum. So now as the pendulum swings from side to side, it draws a line on this piece of paper that you're pulling out, so you now actually can see the time history. Okay? So that this fact that you're recording it on a piece of paper that's moving now gives you the ability to understand at what point in time the strongest shaking occurred and the weaker shaking occurred. And then you also constrain that the pendulum can actually only swing in this direction, so let's say this is the north-south direction. And then you have another one that's at 90 degrees to it that can only swing in an east-west direction. So now you have two records, one that shows you the horizontal motion north-south, and the other that shows the horizontal motion east-west. And so you can now reconstruct exactly what the particle motion was in that horizontal plane at the surface of the Earth. Okay, so that's the horizontal component. And then this is the vertical component. With the vertical component, you have to introduce a spring. So now you have a mass, again, an inertial mass that's on a hinge, and then a spring that's holding it in place. So now when there's vertical motion, this goes up and down. Again, you have a drum recorder, and you can record the vertical motion. So if you want to measure the exact motion of a point, you need to know what that motion is in 3 dimensions, right? North, south, east, west, and up, down. So you need a 3-component seismometer. 2 horizontal components and 1 vertical component. And now you can reproduce exactly what the particle motion was of that seismometer, which includes the 3 components. Okay, so that's how we record ground shaking. Questions? All right. Not quite sure what's going on there. And just to give you a sense of what an actual instrument looks like, this is a typical instrument that we might use today. This is actually a deployment that my group did a number of years ago in Oregon, where we went out and we put out some seismometers for a temporary deployment. So, of course, the Berkeley Seismic Lab runs permanent seismometers across Northern California that stream all their data here to Berkeley continuously in real time, and that's how we detect earthquakes, that's how we generate warnings, and that's how we generate information about earthquakes in the minutes after the earthquake. But in addition to that, you can go out and put out temporary instruments that you might leave out for a few years to record earthquakes for various sort of scientific studies. So that's an example of this. So this is the 3-component seismometer. It's a metal cylinder. It's got a diameter of about 6 inches and a height of about 12 inches, 1 foot, 30 centimeters. Sorry, we're supposed to be decimal, right? I mean, not imperial. Metric. Thank you. Jeez. Okay, so it's supposed to be metric. So this is 30 centimeters, and this is about 15 centimeters. Okay, and so these three component seismometers are actually in this bottom piece of this seismometer, and then this top piece is a slightly different color is actually the digitizer. So it takes an analog electric signal out of the seismometer and converts it into a digital signal that then gets put in. This is essentially just a computer disk in a fancy case so that it doesn't get wet. We would then create vaults. We would dig a hole about 3 feet deep, put a vault in there just to keep the dirt away from it, and then we would put the seismometer in here and then bury it again, and then use things like solar panels to power this instrument. We would put this out, we would leave it there for 2 years, and come back at the end of 2 years and collect the data. Okay, so that's how we would do that. Okay, I'm actually going to stop here, and on Tuesday we will start by talking about how we use these seismograms to locate earthquakes.
You can't fix this.